the second part of the fundamentals of ImageJ/FIJI workshop. So for those of you who attended the session in March, we went over the very basic functionality of ImageJ. I'll just at the start of this, I'll go over it very quickly, just so you can sort of see what we did. So this will be sort of moving on from that to more of the analysis part of FIJI, rather than sort of just opening up images, although that will be part of it. I'm having 4 screens, just trying to navigate them. I have started the Zoom. So yeah, an acknowledgement that a lot of this is based on work that Cam Knoll did, who's from the Monash Institute of Pharmaceutical Sciences. So he taught me everything that I first learnt. So he runs a 2 or 3 day workshop, which goes over a lot of the stuff that I do, but it's all a muchness. But yeah, he is the master of all things FIJI and image analysis as well. We'll be using a few sample images. So there's a TEM stack from Julian, who is now at Monash, as well as a spinal cord, stained spinal cord that was donated by Vernice. Not her spinal cord, of course, but one that she has sectioned out. And of course, I am from the bioimaging platform, so any assistance that you need with optical microscopy, electron microscopy, or flow cytometry. Image analysis, we've now moved into histology, so please contact us on bioimaging@latrobe.edu if you need any assistance, even just some advice. We hand out advice for free. If you need advice on sample preparation, imaging, etc., we're happy to provide that. We're on Twitter, we're also on Blue Sky and LinkedIn and all those sorts of things. So if you want to follow us for what's going on, then please do so. Cinema rules. So all of you have your cameras off at the moment, which is great. So mine is off as well. I find it very distracting when you can sort of see people moving around. So also, if you need to ask a question, I'll keep an eye on the chat. So if you do need to ask a question, please type it in the chat. If it's a larger question, then you can either wait until we have the end of session discussion at the end, or just send me an email and I'm happy to answer it through there. The aims of this workshop are to continue learning the basic functionality of ImageJ and build upon the skills we've learned in the introductory workshop. And also to continue getting an idea of the vast amount of processing and analysis capabilities available. So FIJI is very vast. Even the things that we can see in the software at the moment aren't the extent of what it can do. There are all sorts of plugins and functionality that you can install to increase the functionality of the software. As it's an open source system and the community for FIJI is huge, people are always writing plugins and scripts and things like that. You'll often see them in papers when you're working, when you're reading through. We used XY plugin, or we wrote XY script that you can then request. Often they are freely. They're usually, I've never seen any that are actually commercial that you have to pay for. They're typically available because it is a open source system. Most researchers are happy to hand off the script that they've written, with of course an acknowledgement if you do use it for your own research. So the overview will be going, having a quick refresher at the first up. We'll be looking at automating analysis, which will be a large part of the workshop. Then we'll be going over image optimization techniques, so color deconvolution, stack alignment, extended focal imaging, tile stitching, artifact correction, and then if we have time, we'll have a discussion at the end. We're looking at about 2 hours for this, so please bear with me. So part 1, quick refresher. So I'm just going to change it's going to get very annoying. Change the share. Now I remember why I always do this in in Zoom. Teams is very annoying when it comes to sharing. Okay, that one. So if you open Fiji, it looks something like this. I'll grab some images. It doesn't matter what image we're going to be using. So you should all have access to the drive. If you don't, then you'll need to request access from me. Let me just check if there's anyone has actually requested access. No, great. So I'm going to open up this, and I'm just going to open up 3-channel fluorescence, and let's just use the nucleic acid drag and drop. So regions of interest, we're using a few regions of interest today. So the region of interest bar is up the top. I'll use the magnifying glass. So you can use region of interest to isolate specific areas for analysis, or even just it shows no files available. Can you show the link again? Okay. All right, let me just find where it is. So someone's having issues with accessing the data. So I'm just going to see if that is you as well. I'm just going to send the link through again. Resources part 2. Share. So I'm just going to share the link with everybody via email. Okay, so I've just sent everybody an email. If you don't have access, just let me know and I'll fix that. And there's definitely files in here because I can see them. So the ROIs allow you to isolate areas for analysis. They come in all shapes and sizes: circles, freehand, polygons, of course. Up here, you also have your multi-point, so you can manually count things if you really, really want to. But we'll be moving away from that in this session to more automated analysis. I think it's Control A deletes everything there. You can do text. You can use magnifying glass. You can use the little hand tool to move around. On the top of the ImageJ window, you'll have data depending on the position, the value. In the top of the window here, you'll have display data. This image isn't calibrated, but if it was, you'd see the calibration data there. I can tell that this image is a 1600 by 1200 pixel image. It's 16-bit and it's this size. Now, if you wanted to use multiple ROIs, you can use the ROI manager. So if you draw an ROI and click Control T, it will automatically add it to the ROI manager, and the ROI manager will then open. So then you can now start adding. So there's a little add button there, add. So that when I click show all, it actually shows all of those ROIs. I can modify them, and I find it easiest to modify by going to labels and selecting the number. That gives me basically a pickup point for each of these objects. So then I can click this and click update, and then those positions, because if you move it somewhere else and then select it again, it's actually okay, they've changed it. It automatically updates. It didn't used to do that, and there you go. So now it updates automatically. Oh no, it didn't. Okay, so there we go. Yeah, okay, so you do need to move it and then click update. And then that will be now in that new position. Thresholding and binary functions. So we'll be using a bit of thresholding. So thresholding involves isolating specific pixel values in order to then analyze them or filter. So Control-Shift-T brings up the threshold window, and that allows me, by using these red pixels, to isolate specific areas based on the pixel value. So once you have created that threshold, you can then click, if you need to create a binary image is either black or white, which we can use as masks. You will click apply, and now you have this binary function, which can then be used for masking cells and objects and things like that. And we'll be doing a bit more of that. For measurements, simply doing a measurement is clicking Control M or the Analyze Measure tool, which will analyze the whatever values we've set up. So if you remember, you can go into Analyze Set Measurements and choose the functions, the measurement values that you actually want to measure, area fractions and areas and things like that. And then we can, so if I bring that image up again, so if I isolate this very small area down here and I click measure, it will now tell me the mean intensity, the minimum value, the maximum, the integrated density, remember, is the total intensity, which is in there. Now, if I move that to a different spot and I click Control M again, it should give me a somewhat different value because I'm in a different position. All right. So very, very basic overview there. I have to do it this way because Teams doesn't let me isolate areas and move it around like Zoom does. Okay, so we're going to move on to automated analysis, which can save us a lot of time. So we've already gone over this. We've set our measurements by going to Analyze Set Measurements, checking the functions that we actually want to measure. By using an ROI, we can isolate that area and then measure just in there. We can use the ROI manager to store different regions of interest, analyze a single one of them by selecting on it and clicking measure, or selecting multiple ones and clicking multiple measure to analyze all of the ROIs all at once. And the ROI manager, we've already just gone over. You can store as many ROIs in there. So adding, deleting, renaming them if you want to keep track of them. These are just coordinates, the name that it automatically gives it. And then by going to more, and so by selecting all of those ROIs and then going more and then multi-measure, you can measure all of the objects at one time. So what we can do is by using thresholds, we can limit the measurement just to that particular area rather than using an ROI, although we can use an ROI in combination, but by using a threshold and limiting to the threshold, we can then measure just a particular area. So if I go back to image J and I get rid of that ROI and I use my Control-Shift-T and measure that, but I need to make sure that in set measurements, I am limiting to threshold. So I'm going to limit to threshold, and I'm also going to select area fraction. That will tell me the percentage of the image in which the threshold has occurred. So now if I go OK, and I now measure this, it will show me that the nuclei, as I've thresholded them, take up nearly 4% of the image. And they are this much, the mean value is that, the total intensity of those pixels is that. So it gives me the ability to isolate that. Now I can then combine that with an ROI. By drawing an ROI around this particular cluster, I can then measure that, and I get a slightly different value. Now it's taking up still about 4% of that value. Now what's gone wrong here? It's my ROI manager. Okay, I'm just going to delete all those, delete yes. I'm going to add that ROI. And then I'm going to select that ROI, and I'm going to click measure. And now, why is that doing that? Should be giving me a different value. Sorry, I'm just not sure why that's doing that. It should be giving me a different value. So if I select that small area, approximately what, 30% of that? There we go. Okay, actually 15%. So 15% of that value is of that threshold is taken up within that ROI. So that allows me to isolate both using a threshold as well as a ROI to isolate that measurement from the rest of the image. So by isolating those values, you can get those measurements very specifically. Unless you want a binary, don't click apply. So you can just use the adjust the threshold and then close the threshold window and then measure based on that threshold. You don't have to click apply to make it work, unless you want that binary image. So often we have to choose whether we're going to manually analyze manually analyze a image, or we're going to try and do automatic analysis. So of course, the most accurate method is to sit there and count them manually. However, in practice, that's far too time consuming and can actually get pretty biased. If you're sitting there for hours and hours and hours over long periods of time, you can actually get lazy, and which leads to inaccurate measurements. So it's often easiest to actually set up an automated analysis in order to it may not be as accurate, but in a large enough sample size, it's actually like per image, it may be not as accurate, but over a large enough series of images, it's probably more accurate. So we've already gone over the multi-point tool. So if you click on the multi-point tool, you can literally just count objects and you'll get a result based on the number of objects. Each one of these little spots has a number, so it keeps track of it as you're counting along. To make life even easier, you can use counting grids. So under Analyze, Tools, and Grids, you can actually make a bunch of grids across the image. And then instead of counting all the cells, you can count every third grid, which will give you approximately the same value when you multiply it out. So if you select every third grid, you just multiply your value by 3, and that should give you roughly the same value. But I'm fairly lazy and I prefer to do things, make the software actually work for me to do things automatically. Now, beware, the software is only as smart as we program it, and we aren't perfect programmers. If you can't tell one object from another, odds are the software will have a similar problem. So if you have a massively confluent cell culture and you're trying to count nuclei and you've got cells on top of cells, it's very likely that you will not be able to see what is a cell, and the software will not be able to see what a software will not be able to count the nuclei. So you need to make sure that your tissue, your sample, is actually suitable for analysis in the first place. Now, you should always change this setting before you start. So if you go into binary options and turn on black background, that's a function that you should automatically turn on. So I'm just going to close all this stuff. So if we go into process binary options, you should turn on black background. Now, the reason you would do that is because ImageJ, for whatever reason, by default, automatically inverts the lookup table, makes the blacks whites and the whites blacks, which can be very sort of misleading. And I don't know why. I'm sure there's some reason why it does that, but I don't like it. So I always turn on black background so it keeps the black background of a fluorescent rather than making it white. Maybe it's a contrast thing. I don't know. So Okay. So binary images. So we've looked at binary images very briefly, but essentially binary images have a bit depth of 1. So what that means is 2 to the power of 1, which means 2 colors, which means black and white. So essentially that allows you to distinguish what is an object that you're interested versus an object that is a background image or you're not interested in it at all. So to make the binary image, so what we're going to do is we're going to open up nuclear blue in part 2 demo images. So nucleus blue 2 for whatever reason. So just drag and drop that. And that gives us a nice little sea of nuclei. Now, what we can do is what we did before is Control-Shift-T or Command-Shift-T if you're using a Mac. Control-Shift-T, which will bring up the threshold. Now, you can manually adjust this. So you can see if you go too high, it actually oversaturates. So be very careful of that. So you want enough coverage, but you don't want too much coverage. So try and sort of get it to a point where you start seeing things like this, cells being pinched off. And you'll see why we do that when we start doing watersheds. It just helps a lot with separation of samples. So I'm going to sort of make the threshold so that you sort of, when 2 cells are very close together, like that, then you sort of still see that pinch point. That gives the software something to segment the cells when we get to that point. And then we're going to click apply. So apply will now change it into a binary image. So the background is black and the cells are white. Watersheds. Now, watershed is an algorithm that looks at the sort of the circularity of objects and determines if that is one object or multiple objects. So that's why we have that little pinch point there. So it's actually got something to aim for. So if we go here into process, binary and watershed and click that. Now be aware it is a very dumb function. There is no settings that we can change. It is literally just what it is. And it can go very, very wrong. So if it works, that's great. If it doesn't, then you may have to segment things manually, which is a whole thing. So if I go watershed, what we can see is in our cells that were connected, we can see this has been cut through. So if you don't have enough of a pinch point, it's really got nothing to sort of detect as a separate image. Now, if I look around, I can't really see any that it hasn't worked for. If you find that it hasn't worked for whatever reason, you can just use the paint tool. So if I sort of pretend that this is a non-segmented cell, I can go up to here. If I click on here, I can choose black as my color. So if you hover over the very top corner, you'll see it sort of say black, and you click on it and that will give you black as a color. Then you can come over here and choose usually the pencil tool, double click on it and it'll give you a width. Now I usually prefer a pencil width of about 3. 1's a bit too small because it's a bit, you'll see when you sort of draw, if I do that, even with the jagged, so if you have a jagged sort of line, you can sort of see there that even though it's technically the line has gone through it, because it's only 1 pixel, it's still not segmented correctly. So at least double clicking on there, on the pencil tool, make it at least a 2, and that will actually give you a bit more width to then segment that out specifically. Now, hopefully it doesn't come to that. If you've done your thresholding right, it should be okay. When we move to AI segmentation, it gets a lot easier. But if you're doing this sort of watershed type segmentation, it's a bit more troublesome. Manual watershed. Now we're going to do automatic object counting via the analyze particle function. Now the analyze particle function is a great tool. So if we go into analyze particles, So we can filter based on size. So we give it a high or a low. Circularity. So if we want to sort of look at more rounder objects versus more flatter, sort of straighter objects like lines and things like that. And then we can have different outputs. So you can show overlays, an overlay mask. So a mask just like this, but filtered out by objects, bare outlines, ellipses, masks, etc., etc. So we'll go over a few of these. And then you've got some functionality here. So display results is great if you want to measure all of these objects. So if I turn on display results, it'll give me an output of the measurement while it's doing its analysis of particles. Clear previous results. If you've done previous results, you can just clear it out. Summarize it. So if you want a total number of cells, you want the means, the mean size or mean intensity, you can do a summary. Add to manager, I like to use because it adds an ROI to each one of these objects into the manager, which you can then do other things. Record starts, I very rarely use that. That's if you're doing macro programming, so you can start the macro recorder. We'll probably look at that a little bit more in part 3 and definitely in part 4 when we actually start doing scripts later on in the year. Exclude on edges, I like to use because I don't like to analyze partial cells. So anything that's on the border here is ignored, essentially. You don't use it. Include holes. If you've got holes in your threshold, that could be a bit problematic. I typically don't include the holes, so I just sort of leave that off. Create an overlay, creates an overlay based on the ROIs. I typically don't use that. Composite ROIs, I can't remember what that is. I think it combines all the ROIs into a single ROI, so I don't like to use that. So what I'm going to do is I'm going to click OK. And what do we get? We get an image with a whole bunch of ROIs and a count for each one of these ROIs. We get a results table with the measurement of each one of these objects. So we get a full table of every single object in this window. We also get a summary. So there are 255 objects that it's counted. The total area is this. The percentage area is that 4.5, which we found before. So that gives me a great little tool. And then we have our ROIs. So each one of these objects now has an ROI attached to it so that we can then use these for other tools. And you can see it hasn't touched the ones on the edge, which you can do if you want. I just prefer not to not to analyze partial objects. Then if you want, you can actually output a mask or whatever you want to do. Now, if you look very carefully, you may find things like this, little objects which have been thresholded. Let's see if I can find a little spot. I think I've done a pretty good job on the threshold. Let's turn off the labels and see if I can see anything. No, I think it's done a pretty good job. But if you have little tiny annoying little objects like this, you can just filter those out by using the particle analyzer. So I'm going to delete all of the ROIs. Yes. And I'm going to go to analyze particles, and I'm going to change my size based on pixels to 50 to infinity. So any object which is smaller than 50 pixels is ignored. I'm not going to bother with the circularity because these are all pretty circular anyway. And then I click OK. I don't want to save my previous measurements. And now you can see that these objects here, which were previously counted, are no longer part of this analysis. So it allows you to filter out based on the size. And now instead of 255 objects, we've got 244 objects. Display results. Yep, that's fine. Okay, using masks to aid analysis. So often we use masks to isolate specific areas automatically. So we can isolate we can use the mask to isolate objects in the original image. So if I wanted to, for example, I'm going to open up the original nucleus blue image. Now, if I wanted to get a analysis of the intensity of all of these objects, I couldn't do it in the binary image because these are all just plain white. Because I've thresholded out and I've basically made my signal a signal either black or white. I can't analyze this image and then get those pixel values based on the identical object here. I can't get this sort of variation. But what I can do is I can use this as a mask and refer back to this original image. So if you go, so I'm going to delete all of those objects. Delete all objects, yes. So if I go back into analyze set measurements, there's a function down here, redirect to. Now I'm going to redirect back to nucleus blue 2-1. So any image any object which is analyzed in this uses the identical location in the original image to instead measure the intensities and things like that. So if you sort of had a look here, the mean intensity of the pixel values is 255 because it's an 8-bit image. The bright pixel here. So if I hover over, if you have a look at the ImageJ window and I hover over one of these, every single pixel has an intensity value of 255. So they're all going to be 255. So that doesn't help me very much. So if I redirect the analysis back to the original data by going analyze particles, I'm going to leave everything the same and click OK. I don't want to save the previous measurement. No, no particles detected. Oh, I know what I've done. Okay, what I did was I think I've accidentally created a single ROI somewhere in here. So nothing was detected because it's being directed in some ROI that I've accidentally clicked there. So if you ever get that error, what you do is you go into Edit, Selection, and select None, or Control-Shift-A, which removes any ROIs that might actually be hanging out in the background. So Control-Shift-A, and let's try this again. Analyze particles, and okay. There we go. So now it's actually worked because I'm actually doing the entire image. And we can see the difference here. So that's the one that we did previously. I'll just delete that. So the mean intensity of the binary image that we were doing before was 255. So that's every single object has a mean intensity of 255. Now this is a 16-bit image, so the maximum pixel value we can get there is 65,000. So the mean intensity of every single one of these objects is instead 18,000. So we get that vast difference from actually analyzing the original data. So redirects is really good. Now, just remember to, when you sort of move on to something else, to redirect it to none, because you don't want to then it's an error. I can't find this particular image if it's not there. Okay. So automatically generating ROIs, we've already done that. So we've added to the manager. We add our ROIs to our manager. Now, the beauty of that is then we can use those ROIs. So if I bring my ROIs up, ROI manager. So there's the ROIs that I've created using the particle analyzer. Now, if I then grab another image from my 3-channel fluorescence folder, let's say cytoskeleton green, and drag and drop that. So this is an identical area, but just a different channel. What I can do is by selecting this image, turning the ROIs off and then on again, they actually appear in the new image. So if I wanted to analyze the amount of signal from the green channel within the nucleus, I can use those areas on a different image, on any image, so if I pull in the mitochondria, if I want to know what the signal in if there is any mitochondrial signal in there, you can just turn that off and on, and it will give you the identical area in those ROIs that you can then measure. So if I select all, control all, and do multi-measure, 1 row per slice. I'm not going to do 1 row per slice because there's only one slice, and what that will do is all of the analysis will appear on one single row of my spreadsheet. So I'm going to turn that off, and OK. And now I have analysis from all of this, all of these areas in my mitochondrial red across all of these values. All right, cell segmentation. So we've been using the nucleus and thresholding that and isolating that via a watershed. Now, you can't do that on an image like this. You can't watershed your way to segment all of these because they're all on top of each other. There's just literally no way. If I try to threshold this now, it's just a mat of cells like that. However, we can use the separation of the nucleus as a marker for where the borders of each one of these cells actually are. And that's what we can do in the next step. So we're going to use a function called find maxima. Now, find maxima, you can think of each nucleus as a cylindrical pyramid with the borders around the end and then the brightest point in the center. And what find maxima does is it finds the brightest point within that particular structure and then marks it with a marker. So you can see with each nuclei, what it does is it finds each point. It finds the central point between each of those nuclei, and then essentially segments it from everything else and creates a map. So let's grab I'm just going to close everything just to clean up the desktop. File, close all. Nice and clean. So what I'm going to do is I'm going to open up that nucleus blue image like that. And I'm going to go into process, find maxima. So that brings up this. Now the prominence you can kind of think of as like a filter for intensity. The lower the value, the less accurate it is. So what we do is we find the correct prominence in order to segment this correctly. Now, in order to do that, I'm going to click Preview Point Selection. Now, this is going to be everywhere because the threshold, the sensitivity is very, very, I suppose, low. It's essentially putting a pixel, putting a marker on every single pixel that it can find. So what I like to do is essentially just go up in zeros. So 1, 10, 100, 1,000, I'm getting there. 10,000, almost there. Now what I'm looking for is essentially one spot per nuclei, and I'm getting very, very close. That's pretty good. I'm pretty happy with that. I might go a little bit higher. Maybe 11. No, that's too high. So 10,000 is pretty good. So I've even lower actually. Let's go 9. I'm looking at this guy. So he's that's obviously 2 nuclei, but he's only got 1 spot. There we go. So 7,000 looks okay. 6, 5. That one's got 1 now. Yeah. So okay, I'm pretty happy with 5. 3's too much. So I'm going to go with 5. 5 seems to be a good compromise. I've got most of these connected. So this would be what we would do instead of the histogram. No, the histogram, the watershed, I should say. So the watershed works in a similar way, but we're going to use this as a way of doing that as well. I'm just going to see if I can get a better value. 57. All right, I'm going to stick with 5,000. 5,000 is pretty good. So what I'm going to do now is I'm going to select, now you can again exclude maxima on the edges. So any maxima that appear on the edge, you can exclude that, which I'm going to do. Strict is a little bit more accurate, but takes a little bit longer. I'm going to do that anyway because my computer is pretty fast. So the output type, what I'm going to do is I'm going to use segmented particles. So same as what we did with the particle analyzer, it's going to segment the objects and essentially create a map of where the segmentation is for this. So I'm going to click OK. And it's going to think about it, and it's going to create a map for where it thinks the borders of all the cells are. And there we go. So that gives me an area. So if I overlaid all of these nuclei, what you'd expect is each one of these nuclei would be in the center of all of these objects. Now, this isn't perfect because you can actually see in here, there's a big space, whereas that big space isn't here. So there's obviously no cells in that area. So we're going to have to tidy this up again, up a little bit. So what we're going to do is we're going to take the cell, so this is a cytoskeleton stain, but it can also act as a cell area. It shows me where the cytoplasm is. So what I'm going to do is I'm going to grab that image, cytoskeleton green, and I'm going to threshold this. So threshold this and find where the cells actually are. So we're going to threshold this and find a sort of a good point, maybe there. That looks pretty good. And I'm going to create a binary image. So now I have a binary image. So you can kind of see that if I sort of overlaid this with this, that would allow me to find which parts of these are actually cells and which part of these are actually background. And that's what we're going to do using the image calculator. So the image calculator is essentially it's mathematics. All of these pixels are numbers, and we can use the image calculator to subtract, add, divide these numbers between two separate images. Now I'm going to use the AND function. Now what that is it shows between the nucleus blue image and the cytoskeleton green image where there is a pixel that occurs in both of those in the exact same place. So in effect, it will show me where there are cells and where there is background. So I'm going to go into Process, Image Calculator, and then I'm going to choose my images. So I'm going to choose Nucleus Blue 2 Segmented, and I'm going to choose Cytoskeleton Green. I'm going to choose the AND function. Now, you could probably use the subtract function. That would probably work as well. I just prefer using the AND function. And I'm going to create a new window. The reason I'm going to do that is if I've made a mistake, then I'm stuck with an incorrect answer. But if I create a new window with the result, these two images will stay behind, so then I can try again. So now if I go create a new window, okay, then I get this. Now you can see that the two images have effectively been overlaid, and I can see where the borders of each cell are and where the background is. So now this has given me a nice map in order to determine where a cell background, a cell might lie. I'm going to use the fill holes function to fill the holes in the image. So if you look sort of carefully here, you can see there's some holes in there. Now, again, this can go very, very wrong. Sometimes it can fill in actual big masses of holes. Most of the time it's pretty good, but it can go very, very bad. So I'm going to take this with a grain of salt, but I'm going to go Process, Binary, and Fill Holes. And that's now filled in a lot of the little gaps. Maybe not there, but more or less it's filled in a lot of the little holes that were over there. If I undo that, I can't undo it. So that will fill in any sort of holes, and it makes my my life a little bit easier. You can, again, paint in the holes if you want, but sometimes it's just a bit more work than it's worth. So now I'm going to go back to my analyze particle function. So what I'm going to do is I'm going to create an ROI around each one of these objects. So window, Is my ROI winner? No, my ROI manager is closed. I'm going to go analyze particles. Now, what do I want from this? I'm going to stick with my 50 to infinity filter. I don't want to display the results. I don't want to clear the results. I don't want to summarize. I just want to add to the manager, but I am going to exclude on the edges because, again, I don't want to analyze partial cells. And then I'm going to go OK. And now we have all of our ROIs around each one of these cells. So each one of these should now be a cell. So if I now reopen cytoskeleton green, the original one, and I click show all off and on again, effectively that has now created a segmentation around each cell, which will then let me do my analysis. So I've segmented each one of these cells by using the nucleus as a marker. Now, sometimes it's not perfect, but so what you can do is if you sort of see, oh, actually, that's not great, you can select and delete. Oh, that's not what I wanted to do. Select and delete those objects. And then just manually draw them in if you really want to be that pedantic. And then add it as an object. That's probably not real, but that's all right. So you can also go back to the original nucleus image as a check and then add that to there. And what you should really be seeing is one nucleus. So there's obviously an issue there. So we could go back and do some watersheds and do some filtering and things like that to make this a little bit better. But I'm always happy with 95%. If I can get things 95% right, then that's just saved me a whole lot of work. So what you're effectively doing is looking around and making sure you're approximately 95% correct. And I think we are. I think we've done pretty well. So from here, we can use these ROIs to then effectively analyze all of these cells individually. I might want to see what the intensity of the mitochondria are. So if I open up mitochondria red, then I can do show all on and off, remove the labels, and then I can use this to then, so if I select all my ROIs, and do a multi-measure. No, not one row per slice. So now I would get the area of each cell, the mean intensity within each cell. Now I can then combine that again with a threshold. So if I go Control-Shift-T, I can then threshold the nucleus signal and just measure that in combination with all of these ROIs. Stop doing that. Multi-measure. So now that would allow me to essentially isolate that signal to make my analysis a bit better. All right. So yeah, so checking the segmentation effect, it's never going to be 100%. Effectively, go through your image, check that you've actually achieved at one nucleus per cell if you can. There are some other things we can do, filters and things that can allow us, can help us segment that more efficiently. We can use the watershedding if we want to. However, in this day and age, AI is all the rage. So what you can use is, instead of doing that the hard way, and I like to show people the hard way before I show them the easy way, you can use a function called Stardust. So Stardust is an AI segmentation algorithm, which is very, very easy. It's been trained on both H&Es as well as DAPI stained nuclei in order to segment out nuclei very, very easily. Now, installing Stardust is a little bit of a thing. So essentially what you would do is go into We'll go through it together. So you would go Windows, help, I should say, help, update. I'll give you this PowerPoint afterwards, so you'll have the details anyway if you want to do this later. So updating you should do automatically anyway, every time you open up ImageJ, but this allows you to add more functionality. So as I said before, most of the functionality that is available for FIJI as a default software is not actually in there. You can go in here and add different functions. So there are a whole lot of functions that aren't actually even selected in here. So what you would add to add Stardust is you would need to select where is it? CSB Deep. You would add Stardust, which is down the bottom. Stardust, and then you would click Apply and Close. You should see a bunch of extra sections, selections there, and then you would click Apply Changes. It would download that functionality and install it for you. You will need to restart FIJI, but then you should then see Stardust in as a function available in your plugins. But there's heaps and heaps of plugins that you can download that you often see in papers. So I'll just very quickly go over Stardust, and it doesn't really require, Stardust is actually really easy to use. So I'm just going to open up the Nucleus Blue again. And all we do is we go into Stardust 2D. And we'd select the model based on fluorescent nuclei. You can do H&E nuclei as well, but we're dealing with fluorescent nuclei. Now you can change the sensitivity of these probability scores and overlap threshold. It's all a whole thing. It's really a bit of modification. I always find just the standard default. So if you just click default, restore defaults, that's perfectly fine. If you're not getting the selections that you really want, if it's not working correctly, which it should, then you can mess around with that. I typically don't. So if I go OK, it's going to run this network. It does take a little while because it's running off, I think it's running off a server somewhere. And there we go. So that is the analysis. The colors mean nothing. The colors are literally just there. It's a random, just to sort of distinguish one from another. But this has essentially created a map, and it automatically creates ROI. So if I click Show all of those nuclei have now been selected much, much better than we ever managed to achieve within the by thresholding and watershedding, doing all those fun things. Fine Maxima, it is much, much better at doing it than we can. So I use Stardust now as standard, but it's always nice to know those other sort of more manual functionalities that are available. And you can absolutely do it on H&Es as well. So if you have an H&E histological image, you can use the trained function, which works very, very well on H&E nuclei as well. Yeah, Stardust is really good. All right, part 3, image optimization techniques. So we're going to go through a few 5 different ways of making your imaging better by using functionalities to align, to stitch things together, to correct for artifacts, to make our imaging a lot better. So first up is color deconvolution, also known as stain separation. So normally we would use fluorophores, so fluorescent labels and stains and things like that. But if you're using things like H&E or DAB, those are known as chromophores, so they're colored stains. Now, they're often difficult to analyze because we typically take the image as an RGB image. We don't take them as separate channels like we would for DAPI and FITSI and TRITSI and things like that. So what we can do is we can use known stain, what's called a stain vector, which is essentially just a color identifier to separate things like H&E or DAB from or HDAB and things like that into separate channels for analysis. So it's very, very simple to use. We use image, color deconvolution. So I'll just do that quickly. So if you want to, in the part 2 data file, grab DAB color. So DAB color. And so this is a DAB, an HDAB. So we've got hematoxylin, which is stain the nuclei, as well as DAB, which is used to identify protein localization. So all you would do is go into image, color deconvolution, and that brings up this. Now so these are our stain vectors. So there are a whole lot of different pre-loaded stain vectors, and it's the usual common one. So H&E, they've got an H&E 2. I think you can use one or either depending on the stain intensity. You've got your HDAB, Fulgen, light green, Gemsa stain, fast green, all the way down, mass and trichome, which I use quite a bit for collagen, etc. So lots of different stains. But for this one, we're going to use HDAB. Now, show matrices and hide legends, I typically turn those off because it just ends up giving me an extra couple of windows, which I really don't want. So what it's going to do is it's going to use these known stain vectors to separate this into hematoxylin, DAB, as well as essentially a junk channel. It's a channel which is the stuff left over that it couldn't work out where it was from, and it just puts it in a junk channel. So we typically throw that away. So if I click OK, here we go. So the green is the junk channel. So we can just pretty much just close that. Then we've got the DAB channel, and then we've got the hematoxylin channel. So you can see that it's managed to detect where the nuclei are and where the DAB is. So from here, because this is now, instead of being an RGB image, which you can't easily threshold, we've converted it to a single 8-bit color. We can then use this with our threshold to then analyze the DAB stain. So if I want to isolate where the DAB is, I can use my threshold to isolate where the DAB stain is and do analysis. Now, be very careful with this because stains like DAB are not stoichiometric. So what that means is the intensity of the DAB doesn't correspond to the amount of protein that it's detected. So things like the amount of incubation time that you did with the peroxide, the temperature in the room, the humidity can all affect the intensity of the way that this sort of develops. So it's very hard to actually compare this image to any other image for doing that sort of analysis. However, you can do area. Area works very well. So if I do a set measurement and I do limit to threshold, I don't want that, but I want area, and do a measurement here, it tells me that 25% of this area is made up of DAB. So that I know for sure. 25% of this particular tissue is localized with the particular protein I might have been trying to isolate. Now, you can also do something else with this and make it into a fake fluorescent image. So by inverting the color, so Control-Shift-I, and on both of them, Control-Shift-I, and creating a different color. So I'm going to turn this into green. So if I use my lookup table and change this to green, that effectively turns it into a fake fluorescent image. And I can do that the same here. So if I make that blue, actually I'm going to make that cyan. Blue's hard to see. So where's my cyan? Cyan, blind, cyan. There we go. So that's a lot easier to see. And so from there, I can use my color merge channels, and I can merge these two into a fake fluorescent image. So if I do my cyan channel as color 1, my green channel as color 2. I'm going to create a composite. I'm going to keep the source images just in case I've made a mistake. And I'm going to click OK. Then we get basically a fake fluorescent image. So you can present that now as that's where the DAPI is. Even though you didn't do fluorescent immunohistochemistry, you can get a sort of a fake image like that. And if you come to my QPath workshop, we do a fair amount of this color deconvolution because that's the way that it does its analysis. Let's close all. Okay. Yeah, so be aware, DAB does not perfectly follow the rules of stoichiometry. Reaction with hydrogen peroxide, the enzyme, is not perfectly linear. So duration of reaction, temperature, presence of other molecules can affect the staining intensity. So yeah, just be aware of that. Stack alignment. So if you've ever done confocal, you've very likely done Z-stacks. Now, Z-stacks on a fixed tissue is pretty straightforward. However, if you have a live tissue, something that's moving around, then that can cause issues. So what we can use is stack alignment, also known as registration, to realign these tissues. Now, it's also a massive problem in serial sectioning. So if you're doing serial sections in either histology or EM, what you would do is you would have your sections across multiple slides, stain them, image them, and then you can then stack them on top of each other. But because of just the way that slides are processed, they're never the exact same orientation. So we can use registration to do this for us. So 3D drift correction. So what we can do is if you've got focusing issues, but you've created a Z stack, what you can do is use the drift correction. I'm not going to go into this. This is something that we'll do in the next part 3. But you can actually use the correct for 3D drift option and essentially bring everything back into focus. What we will do is look at linear stack alignment with SIFT. Now, SIFT stands for Scale Invariant Feature Transform. I don't know what that means. All I know is what it does. This plugin is very computer intensive, and it does take a little bit longer than a bit longer. But it does work extremely well. So let's go into the settings. So plugin, so what you'll find, all of the registration plugins will be plugin registration, and we're going to go for linear stack alignment with SIFT. And there are no images open. Okay, so in our image alignment window here, we're going to grab, which image do we want? We're going to go for the multi-photon stack. Okay. So under registration, we're going to grab the why is that empty? Okay, these are empty. Why are those empty? That's not great. Okay, so that is being emptied out. Okay. I thought I put stuff in there. Okay, my bad. I'm just going to quickly upload those into OneDrive. Are they in OneDrive? Alignment registration. Okay, empty. So I'm just going to go find where those actually are. Okay, uploading. Okay, so those should now be available. So we're going to grab Fish multi-photon stack, and we're just going to load that in. Now what this is as it absolutely sounds. upstairs. Yeah, I'll be up in 3, is that all right? 3:30?
Yeah.
The workshop goes for another.
So you need the image.
I can't do it right now.
Okay. Oh, maybe tomorrow?
Tomorrow. All right, thanks. This is exactly as it sounds. It is a multi-photon image of a fish. Now, if we zoom through, we can see all of the sections. Now, at some point, the fish moves. So you see the fish moves while it's being scanned, and then that's a bit annoying. So there's a little bit of movement there as well. So this is a live fish. So we don't have to put up with that. We can align that using Sift. So if I go into plugins, registration with Sift, now most of this stuff you can ignore. So the different settings are not that complicated. I just find them to be completely superfluous. There's an explanation in the PowerPoint about what each of them does. The default is typically fine. However, there are three settings actually in here that are very important. The feature descriptor size is, for optical imaging, you should use a factor of 4. For TEM, you should use a factor of 8. For the feature descriptor bins, what you should use is for optical images, for most images, an 8 is fine. However, for TEM images, you should use 16. Often with TEM, there's a lot of sort of background noise that you need to compensate for, and so that will help with that. So those two settings are really the only number values that you should really change in here. Everything else is pretty much optimized. But the main setting is what you should be using is the expected transformation. And you have 4 options here. Now, translation. Translation is if you've got movement in X and Y, so up or down, which is what we have here. So translation would be perfectly fine for this. Now, you can use rigid. Now, rigid does the exact same thing, up and down, but also rotates. So if there's some rotational issues, so if you've got serial sections and you've got one on a slight angle, you can use that to help there. Similarity. Similarity is the same as rigid and is the same as rigid body. So X and Y rotate, as well as scaling and zooming. So if you've got shrinkage in your sections, then that will essentially increase the size or decrease the size. Like if you've got shrinkage or expansion, it will optimize the registration to suit that. And then finally, affine. Now, affine will do all of that as well as deform images into trapezoid. So if you've got basically a section which has gone into a weird sort of shape, so one sort of like you've got a gradient, then it will essentially change the size of the edges to suit the rest of them. Now, the further you go down through these, the more computing power it takes and the more that can go wrong. So what I typically do is I start with translation and work down. If translation works, great, stick with that. So I'm going to click OK, and you should always have interpolate on. Interpolate means between the different sections, there's more continuity between the sections. So interpolate should be on. So I'm going to click OK. Now it does take a little while because it has to go through every single section, look at different different features and determine if they are the same features between the above and below section, and then make the appropriate changes depending on the setting that we've set. So you can see that it's going through here, aligning. And we're done. So now if we sort of go to the original image, don't worry about these errors in the console. It's just telling you I couldn't find anything for one specific feature. So if we look at the original data and go through approximately at 90, 80, 89, 90, it had that problem. So if we go to the same area, we now have no movement. It's all exactly the same. And you can typically tell, I'll see if I can do this in 3D viewer. Doesn't fall over. So you might be able to see here. So in the 3D view, you can see the problem there. That's actually thrown off the reconstruction because of the movement. Now in the other image, we shouldn't have that anymore. So that's all now been aligned and it's all nice and smooth. So that's an optical image. But what about TEM? We were talking a lot about the settings for TEM. So if we open up in the image registration, image alignment registration, oh crap, where did it go? Wrong folder. My OneDrive is not syncing for some reason, so I'm having a few issues with that. Okay, so if you go into registration and go to serial EM. Now, if you look at this, so this is a serial EM section. This was, I think this was serial block face EM. So essentially the EM went through and sliced image, slice image, slice image through a tissue, but you can see there is some movement. The image is not identically aligned. So what we can do is again with the SIFT. So we'll go into plugins, registration, and SIFT. Now, from that, I can see there is a slight amount of rotation. So instead of doing translation, I'm going to do rigid. Now, those settings that we were having a look at, so for the feature descriptor size, I'm going to change that to 8 because I'm dealing with a TE image, and the feature descriptor orientation bins, we can go to 16, which should make our life a little bit easier. So now I go, okay. And then off he goes. Oh, sorry. All right, so now we should have a more aligned image. So you can see here, especially this tissue here is far more aligned. Now you can see where it's actually moved. You get these black backgrounds in the back where the tissue, where the image has actually been moved to line up with, especially the original image is usually exactly where it was, and then the remaining images are essentially moved to match up with that original position. So then you can sort of grab a section. I'm going to duplicate that. And then that gives me a more aligned image. Now I could try the other functions like a fiend and things like that, but I don't think it would be necessary. That's pretty much good enough. Now, if we've got some major issues, and I love this next image. Star Trek bridge. So we all remember the old Star Trek where they'd throw themselves around while the camera wildly goes crazy. So there's a lot of movement here. So what can we do with this guy? Now I can see from here, this is mainly X and Y with some rotation. So I'm going to use rigid body. So we're going to go back into registration, and we're going to go SIFT, and we're going to use rigid again, but I'm going to put this back to, so this is more of a an optical image, I suppose you'd call it. So I'm going to put these back to 4 and 8 again, and I'm going to choose rigid and click OK. And we can see exactly how much peril they were really in real life. Okay, so as I go through, you can actually see that it's aligned it pretty well to where Captain Kirk's sitting. You can see that the image wildly goes off to the side when it pans to the right there. So now, if we segment this based on Captain Kirk, you can see that even though there was a crazy amount of movement, we've pretty much stabilized that as well as we possibly could based on the data set from this. So yeah, SIFT is a really great functionality. Extended focus. So moving on from the next step, if we were doing sort of that alignment and things like that, is extended focal imaging, also known as extended depth of field. So EFI, EDF, they are identical. They mean the exact same thing. So some samples are very thick and the focal plane of the microscope is often not wide enough. So what we would often do, especially if we're using wide field, not so much confocal, but more wide field. So if we had a thick sample with a lot of topography, what we can do is, the problem is that you would often have parts of an image which are in focus and parts of the image which are out of focus. So by taking multiple Z stacks through the image in bright field, you can get essentially the entire in focus parts of the sample and then merge them into a completely in focus image. Now, this is where we need to add a new plugin. So in the data folder, you should have a file called extended depth of field. So what you would need to do to get that functionality is to go into your ImageJ folder. Where is my ImageJ folder? Right click. Where is it? Analysis. So if you find your FIJI app folder, wherever you've installed it, and you go into plugins, these are all the plugins that you are typically given when you first install the system. So what you would install the software. So what you would need to do, and I've already done this, is to just grab extended depth of field and just drop it into that folder there, and that will give you that functionality. You will need to restart FIJI. But then when you do, you will have extended depth of field or whatever plugin that you've installed as part of that. Now, there is another way, which was what we did before. So you can click on Manage Update Sites. So you can go into Help Update, Manage Update Sites, find Big EPFL, and then Apply, and that will download the functionality and install it into your plugin folder, like we did with Stardust. So what I'm going to do is I'm going to grab where my folder is. Keep track of my folders. So back into the demo images. You want to go into image alignment, and we want to find EDF. And we're going to grab the spinal cord image. Now, this is an image stack that I took upstairs on one of our basic wide field, bright field images. This is a stack of a somewhat thick piece of spinal cord. Now, as we go through the different focal planes, we can see that part of the image is in focus, but part of the image is blurry and out of focus. So as we move through, we see more of the in focus parts as we move through. So now this is not much help to us if we sort of want to look at it as a single image. So we're going to have to make some changes with our extended depth of field. So let's go into plugins. And we're going to go into, now, have I installed this? I did. It's like I haven't installed it. I thought I did. Okay. Go back out of here, and I will need to do that. So let's go into plugins, and I'm going to open up my analysis. Okay, so I'm going to open up my FIJI app, plugins. I must have reinstalled ImageJ since I last used it. Okay, so drop that into here. Okay, and I'm going to restart FIJI. Eventually. It's where FIJI takes longer and longer to open up. It used to open up really quick, and now it's gotten a bit quite large, and now it's just taking a long time to open it up. That's okay. Right, so there we go. So now in the plugins, we should now have extended depth of field, which we do. So I'm going to open up recent spinal cord, and then I'm going to go into plugins and extended depth of field. Easy mode is perfectly fine. I actually don't find any real advantage for using expert mode. So easy mode, and it is very, very easy. So either you can get fast EDF merging, or you get high quality. So I always go high. There is a bug in here. I don't like to use the height map because I find it completely pointless. It just shows you the different features that it found when it was trying to do this. Whether you say yes or no, it's still going to do it anyway. So I just click. It doesn't matter what you click there, and then I'm going to just click run, and we should get a new image. And all of the sections should be, so there's the height map that just gets made anyway. It's completely useless. So now we've gone from this image, this stack, to this in focus image. Now it will look a little bit washed out, so you will need to do an adjustment. So if you go image adjust bright field, then you can adjust it, the contrast, just to make it look a little bit less washed out. And there we have all of those sections from that Z stack are now in focus and in one single image. So it's very similar to, very, very similar than using a maximum projection on a fluorescent stack. Except this, we can't do that with a bright field image because it doesn't work very well because of the out of focus light. With confocal sections, we don't have out of focus light essentially, so we can do a maximum projection. If we did a maximum projection on here, if we went in the image stacks Z project and did a maximum projection, I don't think it'll work very well. Yeah, so it looks terrible. So we have to use EDF on here. Now, anyone who's used the slide scanner, the Zeiss slide scanner, there is a functionality in the slide scanner here that you can actually turn on EDF. It makes it a larger amount of time to image because you have to do Z stacks on every single part of the image. but the images look amazing. So if you've got topography in your sample, and you need to capture, you need to get everything in focus, then EDF or EFI is the way to go. Right, we're burning through this. 30 minutes left, so I think we might be right on time when we finish. Speaking of slide scanners, tile imaging. Now, if you use the slide scanner, this will do that automatically. It'll take a whole bunch of images across a sample and then stitch them all into a single field of view. You can do that quite simply with FIJI. So sometimes when you take an image, the entire object just doesn't fit into your field of view. So what we often need to do is take multiple images across the sample and then stitch them together in a single image. Now, for best results, you need at least some overlap from one image to the other, preferably 10%. 5% will work pretty well. 1% may work, but yeah, the more of an overlap you have. Now you can do this manually. I did this completely manually with a brain section. So I essentially went from one area to the next area and then down and then across again. But I did leave, you can see there's some doubling up between the sections where there is a 10% overlay approximately, to give the software something to essentially look for when it's trying to stitch. So you can use the simple stitcher, which is a pairwise stitching. All that means is it's stitching two images at a time. So if I wanted to stitch these 4 sections of the brain together, I have to stitch this together, and then the 2 halves together. So it takes 6 steps, but it is absolutely possible to do that. So if we go back into our folder, which I keep closing for some reason. So if we go into the demo images under image alignment and then stitching, you should have these 4 images in here for the brain. So what we can do is if we go into, so if I can align them very, very manually by just essentially aligning them like this. And there's my brain there, but I can do this using software algorithms, which is obviously a better way to do things. So we're going to go into plugins, stitching, and pairwise stitching. So all it asks me is which images do I want to stitch? So I'm going to do 1 and 2. Now, what you can do to make things a little bit easier is you can actually use an ROI and just select the area with the most amount of signal. You don't have to, but it does make things a little bit more easier for the computer. I'm not going to do that because this is a fairly obvious stitch. So if you're having issues, then use ROIs to select parts of the tissue to actually look at to do the stitch. So let's go to stitching, pairwise stitching, brain 1 and brain 2. Okay. And now it's asking me how I want to do this. Now, I usually use linear blending, and it just blends those colors together. You can use an average, median, max intensity. You can do all these sorts of things, and you can try different ones. I always find linear blending is fine. Check for peaks. I usually type my I can't remember what this actually does. Check peaks. Oh, I know this. So you say it's approximately 10%, 10% overlap, but you don't have to do that because you can actually compute the overlap. You don't have to tell it the percentage overlap. You can use the software to compute that for you. I like sub-pixel accuracy, so we're not being accurate to the pixel, we're being accurate to part of the pixel. And of course, you want to display fusion. If you don't do that, it gives you a bunch of coordinates that you can use for scripting and things like that. But yeah, displaying fusion is obviously what we want to do. I'm going to leave that as is and click OK. And there we go. So very, very easy. We've got that. So I'm going to now go to pairwise stitching again. Pairwise stitching again, and I'm going to stitch 3 and 4. And I'm going to use the same settings. And there's 3 and 4. And now we have these two sections, which I can then go stitching, pairwise stitching, and then we're going to stitch that with that. And then we should get the whole brain. There we go. Perfect. So there are no obvious artifacts that I can see. It's worked pretty damn well. So that's one way of doing it. Very manual. However, if you have dozens or hundreds of sections, that doesn't make much sense to do that. So we're going to do things a little bit more automated because that's what we try to do. We've got lots of other things to do, so we might as well make the software do the work for us. So advanced stitching, you'll find in the same folder, the same function plugins, stitching, and we're going to do grid collection stitching. Now, grid collection stitching gives us a whole bunch of options to do. Now, for a lot of these, you have to know the way at which you actually acquired the image. Was it backwards and forwards like this? Was it column by column? Was it a snake? Up like that? Again, I'm fairly lazy. I go to unknown positions. I just make it work it out for itself. But if you do know what it is, it does make life a little bit easier. But I'm just going to go unknown positions and I'm going to go OK. So I'm going to choose the directory where my images are. So I'm going to go browse and I'm going to try and find them. Which is going to take me a while now. Where is my OneDrive? Okay, I'm going to save myself a little bit of a headache, and I'm just going to copy those images straight to my desktop because I can't be bothered looking. It's not finding OneDrive for whatever reason. Copy, and I'm just going to put them on the desktop. New folder, brains. I'm just going to paste them in there. So now I should have desktop brain. So that you won't see anything. We're just literally selecting the folder and I'm going to click open. So now it knows where to look. Confirm files, I like to do that, especially if you have what's called a contaminated folder. Contaminated folder means that you have other files in there apart from the files that you're interested in. So that allows you to sort of confirm that the images that you want are actually the ones being tried to stitch, because you don't want sort of random stuff being stitched into an otherwise obvious brain. Again, I'm going to use linear blending. You can use average, you can use median. I just always use linear blending. I leave all of these as default because I don't want to mess with that stuff. It seems to work always pretty well with this. I don't want to add tiles as ROIs. I want to actually stitch the things. We don't need to invert X and Y coordinates. We want to keep the X and Y coordinates as they are. We don't have to worry about stage position because this is a single plane. But if you do have a Z stack, you can align tile Z stacks with this. You can ignore Z stack positions. Otherwise, it will take it from the metadata. And if for whatever reason between different sections you have different Z positions, it can get a bit crazy. So it doesn't matter what I put here because I've got a single Z position anyway. Again, sub-pixel accuracy, I want as much accuracy as I can. Downsample tiles, if you've got a very large amount of tiles, you can downsample them, which means reduce the resolution. Now, I've only got 4 here, but if you've got thousands to make things move a bit faster, then it may actually be a better idea to downsample. Again, I want to view display fusion. I want it to show me my fused image. Use virtual input images. Slow, even slower when combined with sub-pixel accuracy during fusion. I don't use that ever. I don't think there's a point to do that. Computation parameters. I am going to save computation time, but use our more RAM. Honestly, it doesn't matter. These days, it doesn't matter because our computers are pretty powerful. This function was designed, I think this is about 10, 15 years old. Computers were pretty weak back then, so it doesn't really matter what we choose here. Image output, I want to fuse and display. I don't understand what the difference between this and this is. I just want to do that anyway. So if I click OK, it's going to ask me, this is my confirm. So if I've got a contaminated folder, I can untick images that I don't want to be part of the fusion. Now, when I click OK, what it's going to do is it's going to check, because I've selected unknown positions, it's going to compare every image with every single other image in all positions. So if you've got hundreds and hundreds of images, it can take a while. So it's the sort of thing you want to just click OK and then maybe go home for the night. Like do it at the end of the day and let it stitch overnight, because it can take a long time. But because we've got 4, it's pretty quick. So we'll see it. We can see it there. You can see from the output, it's compared image 1 with 2, 3, and 4, image 2 with 3, 4, image 2 with 4. So it's gone through every single possible, what's the word I'm looking for? Every possible set of images, comparison between each tile, and tried to work out the correct one. And it's done a pretty good job. It looks very, very similar to what we saw with the pairwise. So it's, even though we haven't told it in the orientation that we collected it, it's worked itself out for it. And that only took a few seconds. So then we can save that as a new image. But obviously easier to use the slide scanner. Background artifact correction. Now, it's always best to try and get the microscope set up correctly every single time. So that usually involves setting up the illumination, doing Kohler illumination, the condenser, and I always push that when I'm training people, especially if they're using bright field. But sometimes, even after our best efforts, we can't do much. Now, the lenses that we deal with are circular, which can cause what's called vignetting. Vignetting is essentially like with the Earth and the equator. The equator is always the hottest because it gets the direct sun, but the poles, because of the curvature, get the light more spread out. And the same thing happens with a microscope. We get these sorts of artifacts. So if we do a tile scan, we can get this sort of vignetting effect, which is obviously not great. So we're going to use the image. So we've used the image calculator before when we were doing our cell segmentation, but this time we're going to use the Calculator Plus, which allows us to do extra mathematics while still adding, dividing, multiplying our images together. So what we're going to do, so image artifacts can be caused by improper microscope setup. So incorrect Kohler illumination. So that's probably what's happened here with this image there. Inherent issues with DIC. DIC is a great technique, but often what we get is a gradient from one end to the other of dark to bright, and there's not much we can do about that. Bad tiling setup, if we haven't set up a correct shading correction, etc. Dust on optics, if we've got little spots everywhere, or just plain lens vignetting, which we can't really do much about. So I talked about lens vignetting as the light moves through. Obviously, the center of the lens is going to get the most amount of light, but the edges are going to unfortunately be darker. Now we can fix this. No, I don't. Well, there's not much we can do during acquisition apart from using zoom. So if instead we zoomed in on this area, we usually do this with a confocal. It's effectively ignoring that, but we zoom in here. There's not much we can do. However, after using post-production, we can fix this. So the first thing we need to do in order to fix this is to either capture or create a background image. Now this acts as basically a blank template to tell the computer, by the way, this is where the problems lie. Now, if you sort of, you might see spots on the lenses, spots on the camera, this vignetting effect, or etc. So by using this, it shows the system where the problem is. And you can usually get this by effectively going to an area where there is nothing and then defocusing. So defocusing leaves essentially just a map of what we're looking at with the problems here. Now you can create a background image. It's not great, but you can create, if you're stuck and you haven't done this at the microscope, you can actually create one. So what we're going to do is I'm going to go into the main folder of our image, demo images, workshop resources part 2, and I'm going to get the stage micrometer image. So we use this in part 1. Now this has been collected very badly. You can see the vignetting. This was taken using a 4x lens, which is often the worst because you get, it's a very curved lens and it has a very wide field of view. So what we're going to do first is we're going to use this image to create a background image to show where the gradients are. Now what I'm going to do is I'm going to duplicate this image to create an identical image, and I'm going to blur the living hell out of it. So I'm going to go into process, filters, and Gaussian blur. Now Gaussian blur essentially blurs the data to give a more smooth image. We'll be using Gaussian blurs a lot in part 3 when we do that. Now what we do is we click preview. Now you can automatically see a 2 pixel radius is already blurred it. Now I'm going to blur this even more. I want a massive amount of blur. 30 is not enough because I can still see the micrometer. Let's try 100. That's perfect. So I've effectively got rid of all of the signal from the image whilst retaining this vignetting, and I'm going to click OK. Now what I'm going to do is I'm going to select this entire image, Control A, to create an ROI around it, and I'm going to measure it. So I'm going to go to, but first of all, I'm going to go to, I want the mean gray value of this, and I'm going to measure it. Because what we're going to do is we're going to divide this image by this image and then multiply by the total intensity. So, but the mean intensity. So I'm going to go Control M or M, and I'm going to get a mean value of 124.736. Okay, so bear with me. So now I've got 2 images and I've got a value. So I'm going to go into process, and I'm going to go down past the image calculator to calculator plus. And what I'm going to do is I'm going to use the divide function. So divide will divide every single pixel in one image by the other image, and then I'm going to apply a multiplier to it. So you've got image 1 divided by image 2 multiplied by K1 plus K2. I'm not going to use K2, but I'm going to use K1, and that's going to be this value. So I'm going to type 124.736, and that's going to be my multiplier, because dividing the images together is going to make a very dim image, and by multiplying it by the mean intensity, it's going to bring it up to more of what it was before. So I'm going to select as image 1 my image to be fixed. My image 2 is going to be my background image, which is that one. And then I'm going to create a new image. And if I click OK, then we get this image. And you can see the vignetting is now disappeared compared with one to the other. The basic data is still very much there. But we've removed that vignetting, and you can use that for pretty much at any point. Now, if of course you had actually collected at the microscope a background image, you wouldn't have to create one. You just use that, and then you do the same thing with the image calculator plus, you would measure the intensity of the mean intensity of the background image and plug it into there and use image 2 would be your background image. Now I have another image that's more obvious. So we have this is an image that I have tile scanned, and I have done a very, very bad job of setting up. This was a confocal image, I believe, with DIC. And DIC confocal is always problematic. So DIC, you'd often get this top to bottom gradient. And so when you stitch it together, you see some obvious issues with tile artifacts. What I did at the time was I created a second image in a blank part, and you can actually just see debris around. So I created this in a blank part of the image, and this is going to be my background. So again, I'm going to Control A on this image and measure. Measure. Here's my measurement. Okay. And the mean intensity is 28888. So what I'm going to do is I'm going to come in here, image calculator plus, process, image calculator plus, and I'm going to go 3x3 tile sample. And then my image 2 is going to be 3x3 tile sample background. In K1, I'm going to put 28888. I don't have to put 0.212, but I will anyway. And OK. And there we go. So now this is a little bit darker, but I can use image adjust brightness to bring this up. Oh, what happened there? There we go. And then you can see that now all of those artifacts are removed. Nice and easy. Now, if I do train you on the confocal and you are doing this, I will show you the functionality within Zen itself to do this when you're doing your stitching. It does have an input for putting a background image and removing the stitching anyway. However, you can do that using image J anyway, and just do it that way. All right, that's it. So we've got to the end. Any questions while we're here? Happy to answer anything. If you want to unmute yourself. No, everyone happy? Lost a few people, but that's okay. So I have recorded this, so I will send the recording out. So if you miss something or you want to do anything, I don't know if that fire alarm went off, but what you can do is have a look through. You'll have access to the PowerPoint. If you've got any questions or you want to discuss any projects with scripting or things like that, then let me know. I will advertise part 3 later on in the year. I'm thinking probably August, September. However, in July, I will be doing the first of the QPath workshop. So if you're doing a lot of histology, image slide scanning, like very large slide scanning image, you want to learn how to do segmentation, measurements, and things like that, QPath is a good idea. But anyway, thank you, everybody, and I'll leave it there.